Thank you for the introduction. My train was delayed this morning, so I came in actually around 11:30, so I missed the first half of this morning, so I apologize for that. And thank you for the nice introduction, and good morning, everyone. So I've decided to tone down my title slightly compared to the abstract I've written, because I realized that claiming enhancing drug discovery is too much of too big a title for my talk. So at the end, I go for a title that is probably more suitable for the content I'm going to talk about. So it's about enhancing compound screening with contrastive-fine-tuned sentence transformer. So I start with some very brief explanations about the concept, transformer, language models, molecular embeddings, which will probably be mentioned a few times in the next 2 days. And then I'll share with you my ongoing research, especially with a focus on the contrastive fine-tuning work and how we use it for compound screening. And if I have the time, then I'll share with you another project, which is also relevant to this conference, and that is that we use sequence-to-sequence models for organic reaction predictions. I think it's safe to say that we all feel the impacts of this current wave of AI models. So my daughter, she's 8 now, she is growing up with Alexa. A few years ago, she would ask like cute questions like, Alexa, do you believe Santa is real? Now she's 8, and the other day I caught her trying to ask Alexa to do tricky questions from her homework for her. I think in a way that reflects probably parallel to our own relationship with the current wave of AI models in the grown-up world. So currently there's intensive effort to apply those new wave of deep learning algorithms and models in the broad field of biology and chemistry. So AlphaFold is probably widely used at the moment, and Google has developed a new model to predict the inorganic materials last year. And this person, who has single-handedly probably made a black leather jacket trendy again, is rapidly expanding NVIDIA's team in drug discovery and biology. So we have seen some success, but we're far from seeing the full impacts that AI can generate in the field. So this new way of deep learning models will always rely on big data. So you think about big data in our field, we have plenty of millions of sequences, biological sequences, proteins, DNAs, and we have structured data, small molecules, biological molecules, and we have an enormous database such as PubChem and Think that covers a fraction of the known chemical space. We also have limited labeled data, kind of molecular properties of certain molecules. So in terms of sequence data, they have a strong similarity with language sequences, and the structured data we have similarity with images. So this opens up opportunities to integrate techniques and concepts from other domains, especially in natural language processing and computer vision, and apply those to the kind of questions that we are interested in chemistry and biology. And it's also quite interesting to see tech companies are coming into the research field. But as Andrea mentioned, I'm sure there's some culture clash between the tech companies and the bio companies. If we think about various ways how we can convert molecular structures for machine learning, so on one side, we can use image, and then that can be used for QM calculations and feature engineerings. And then we can also treat it as image and use GNN for kind of image recognition techniques. And we can convert those structures into text sequences, such as smiles and selfies. And there are ways that we break those smiles into substructures, and then we can convert those substructures into vectors for machine learning. So molecular fingerprint is one of the traditional ways that we use to convert those smiles for machine learning. But there are new ways that we can borrow from natural language processing, because smiles or other sequence representations of molecules have strong resemblance to text. Therefore, we can borrow a concept called embedding to describe, as a new way to describe of molecules and the molecular, the chemical space. So within the context of NLP, so natural language processing, the concept of embedding is actually that we train a large corpus of text and to determine the vectors that represents the words. And those the vectors are determined by the context the words are used. So for example, if you have the vectors to describe king and a man and a woman, some elements of those vectors would have something to reflect the feature, the many layers of feature that are associated with those words. And if we kind of plot them in the vector space, you see words with similar meanings, like, for example, king and queen would occupy similar vector space, and man and woman would occupy similar space. And the distance between king and a man and the distance between queen and a woman, which reflects the difference between those two pairs of words, should be similar to reflect whatever is the difference between those pairs. And the revolution comes from the transformer that was introduced in 2017. So previously in NLP, the words are described in their static meaning, so kind of a fixed meaning. So we have mouse as the animal, as one vector, and we have mouse as the computer accessory, that's another vector. So that's the two vectors that separate the two meanings of mouse. But in transformer, it introduced this contextual embedding, where the words are described not just based on a static meaning, but in the context they are used. So now a mouse can be separated as the cheese-loving mouse or the fast-moving mouse. And therefore, you know the context that words are used, and therefore the meaning of those are slightly different. So that's an incredibly powerful approach, and coupled with how fast transformer is, and therefore transformer now is the foundation for all the latest wave of AI models. So we can borrow that approach, and to represent our chemical space, we have enough big data in terms of small molecule space to train these molecular embeddings. So now we have vectors that are more compact than more traditional fingerprint approach, and that hopefully captures the property of the molecules in a way, and then they are related to each other in this embedding space. I think more important is that we can use various ways to train and interrogate those molecular embeddings using deep learning models and algorithms I'll show later on. So the original transformer using an encoder-decoder framework, and subsequently there are many variations based on that framework. So now we have the encoder-only BERT that we can use to do molecular property prediction. So basically any regression task, now we can use a BERT model to do it, and classifications, clustering, and the ranking of and screening of molecules are all possible with the BERT type of encoder-only model. And then if we use both encoder and decoder, then that could be ideally for sequence-to-sequence learning. And that's something we can use for chemical reaction predictions. So that's kind of the two aspects of what we're currently working on. So the way to kind of utilize those models is that we usually need to have a pre-trained model using large amount of data, depends on what application you're interested. So we do the pre-training and get a general pre-trained model, and then depends on what your specific research question is, and you do fine-tuning to make your model specialize in the question you're interested to predict, and you use inference to make the prediction on your test data. And then how you do the fine-tuning very much depends on the amount of labeled data you have. So if you have thousands of molecules with some properties you want to predict, and then that could be a straightforward fine-tuning of the pre-trained BERT model. But what if we don't have that many labeled data? So say if we have tens of molecules or 100 molecules, that is typically from maybe initial screening of molecules against biological data. Then we could use something called contrastive learning. So contrastive learning is a machine learning paradigm that's kind of supposed to enhance more meaningful learning of the embeddings from the model. So if we look at, there are two ways to do the contrastive learning. One's unsupervised. Unsupervised that you don't need any labels with your molecules. And you can do dropout masks apply to the embedding of your molecule, the same molecule, to make a similar pair. So you slightly alter your molecule's embedding to make it as a similar pair. And all the other molecules, you can build them as a dissimilar pair. And you can also do this with the supervised context. So you need labeled data. So it depends on what the label is. You can put similar molecules together and then these similar molecules as another pair. So, this figure actually illustrates both unsupervised and supervised. So this is that if you have a picture of the cat, so imagine it's a molecule, and you can make variations of this cat with only parts of that picture to make it as a similar pair. Or you can just construct a cat and then cat and dog as the dissimilar pair. So this approach is quite useful for classification tasks. So I have to admit, I come to this question completely from the cool tech perspective. Oh, and thinking, as Andrea mentioned, that probably this is cool methodology. Let's try out with some data. So the kind of the flow of the framework is that we first start to train a BERT model with a reasonable number of smiles. 10 million is probably a good starting point. And then we use some mean pooling to make it as a sentence BERT, or represent the molecule at the molecular level, called molecular embeddings, to make the model faster. And then we introduce the first stage of unsupervised contrastive learning, and with something called SIMCSE. It's called simple contrastive learning of sentence embeddings. So the purpose of that is to kind of improve spacing of molecular embeddings from the previously trained model. And then the fourth stage is that we do further supervised contrastive learning with the actual active and inactive molecules that we get from bio-target screening. And then you can use this contrastive fine-tuned model for various classifications and ranking of new lead compounds. And usually, because the way the sentence BERT is constructed, it's very fast. So we can do screenings of 100,000 of molecules in minutes, basically, with a basic GPU. So just to illustrate how this model will work, so with the general model, it can't really separate the active molecule and inactive molecules in your label. And then once you feed it in the contrastive fine-tuned model, the model is learning to separate the active molecules and inactive molecules through a contrastive loss training process. And then we can use this model to do the classification. So it's reasonable classification performance. So this is just to show we have three models. We have the contrastive learning, which is the blue. And we have the green, which is fingerprint-based classification. And we have the orange, which is standard BERT fine-tuning. So if you have enough data, for example, over 100 molecules, there's no contrastive learning really doesn't give that much advantage compared to even just fingerprint-based approach. But if you have limited number of molecules, for example, we have 32 and molecules, then with smaller number of training data, then contrastive learning can definitely learn that thing, something extra in the future in the embedding space to give it slightly better performance. So this highlights its ability and its potential maybe in a more lower data range. And we can, as the model is very fast, so we can do fast screening of a larger number of molecules. So we used a data set from PCBA, just one target, with about 70K molecules, and we can screen those in minutes. And so I think it's able to correctly identify 21 molecules out of the correct 41 total active molecules. And then also the contrastive learning gives slightly lower false positive in compared to standard BERT fine-tuning. So I think this is type of QSAR approach, but now with molecular embedding and coupled with some deep learning algorithms in terms of doing the classification and prediction. I have to admit, this is my first kind of bioinformatics compound screening project because I come from a very computational chemistry reaction mechanism background. So I would appreciate if you have any suggestions or like more relevant data for me to explore, then I would be very happy to chat over coffee. Potentially, we're looking for, at the moment, we're using a very simple BERT model that we can actually increase the complexity of the model, make it more multitask, and then therefore we can lower further the training data range into a more few shot multitask learning approach. How much time do you have? 5 minutes, okay. So the last few minutes, I would like to share with you very briefly of the organic reaction prediction that we've been working on. So we use the state-of-the-art language models, such as Flanty5 and Byte5. And by the way, this is the QR code for the preprint to do reaction predictions. We're interested in various aspects along this pre-training, fine-tuning, and inference process to try to understand the potential of those models on the reaction prediction tasks. So we actually explored various starting point for the model. So you either start from random initialization, which is a disaster. It doesn't have any pre-knowledge. And you can start from the language model. And we can also do further continuous pre-training with additional smiles to make it more chemistry aware. And then once we have the model that is ready for fine-tuning, and then we use the USTPO dataset for training. And then again, the question is, how much data would you need to make it reasonable accurate? So we start with the full 400K, and we kind of do a sampling of various proportions of that data to see exactly what's the kind of percentage reaction we really need to fine-tune those models. And we explore various tokenization strategies. And also we look at different decoding strategies, how the model used to predict the product. And we look at 3 tasks for reaction prediction, ritual synthesis, and reagent prediction. We also use in that preprint something called SHARP, explained by AI, trying to see how the model come to predict those products. So on this heat map type of representation, you can see the sequence of input from your reactant and reagents, and then the x-axis is the predicted product. And you can see kind of how those contribute, how the reactant and reagents contributes to the predicted product structure. And we can visualize it in a way using RDKit, make it more sense, and kind of correlate that with the reaction mechanism. And by the way, that's a very simple SN2 reaction. And we have a few other examples in the preprint to show you. So again, this is work ongoing. So I guess the reflection we have is that sometimes we always see with this kind of models, people would use intensive, like 90 millions of smiles to do the pre-training. And with our model, we realize that it might be beneficial, but it's not essential. So we could just start with a well-trained language model and just fine-tuning it with a sufficient number of reaction data, and that would give you decent performance. And with the very simple model, for example, the Flanty5 small model, you can train it to adapt to chemistry in about 5 hours to be able to do some decent organic reaction prediction. And I just want to share with you a recent message I've received on LinkedIn. Didn't know if I ever received this kind of message, asking me to be the data annotation team and asking questions, identify questions on chemistry and train AI and evaluate the quality produced by AI. And I realized that this is very much related to a news I've read a few years ago that OpenAI was in a scandal that they hired some Kenyan workers with very, very low pay to train ChatGPT to make them less toxic. So definitely there's some parallelization there that we are being used as just in the same way as the Kenyan workers, probably to try to be part of that reinforcement learning training for AI models to be better at chemistry. So those are my students and collaborators, and thank you for your attention.
So do we have any questions?